So finally, let's discuss the actual firing of the neuron, the action potential. So the action potential is just a brief electrical charge that travels down the neuron's axon. So obviously there is no real little man residing inside the neuron. Instead, there are what we call voltage-gated sodium channels, which open when the threshold voltage of negative 65 millivolts is achieved at the axon hillock. These voltage-gated sodium channels are located all along the length of the axon, but initially only those that are at the axon hillock open. When this occurs, a large amount of sodium rushes into the neuron, causing the voltage to go from negative 65 and jump up to positive 50 millivolts. This spike of positive voltage is the action potential. So here we can see that the voltage at the axon hillock is moving towards threshold at negative 65 millivolts. When it reaches threshold, the voltage-gated sodium channels open. So these channels are voltage-gated in that they open when a certain voltage is reached. You may recall that there are other channels on the dendrites called neurotransmitter-gated channels that open when the neurotransmitter bonds with the receptor. These voltage-gated sodium channels open, allowing sodium to rush in. Because the sodium is positively charged, and because there are so many sodium channels, the sudden influx of sodium jumps the charge inside the neuron to positive 50 millivolts. As this is occurring, the increase in voltage here triggers other voltage-gated channels further down the axon to open. This allows more sodium in at this location. Notice that when the positive 50 millivolt charge is reached, two things occur. The next set of channels opens, and those closest to the charge close. The sodium voltage-gated channels close, allowing the charge to reduce back down towards zero, and then eventually to negative 70 millivolt resting potential. Sodium is pulled in, and then pumped back out, and in this way, the negative 50 millivolt charge of the action potential moves down the length of the axon. The size of the action potential stays at positive 50 millivolts down the whole length of the axon, regardless of how long the axon is. Thus we say that action potentials are non-decremental, unlike EPSPs or IPSPs, which lose their intensity as they move through the dendrites and the cell body. Action potentials are non-decremental because they self-perpetuate in the manner shown. This holds true even for axons that branch many times. At the end of each branch, when the action potential arrives, it's still positive 50 millivolts. Action potentials are always the same size. If they occur, they are positive 50 millivolts. They're not positive 20 sometimes or positive 80 other times. This is to say that the action potentials are all or none. Another subtle point shown here is that the local environment near the axon hillock has returned to its resting potential as the action potential travels down the axon. Two processes are primarily responsible for returning the axon to negative 70 millivolts. The first is that shortly after the sodium ions begin to flow into the axon, the depolarization that they produce triggers voltage-gated potassium channels to open. These channels have a somewhat higher threshold than sodium channels, so they open after the action potential is well underway. Consequently, positive potassium ions begin to flow out of the axon. This removal of positively charged ions begins to push the voltage down towards zero and back into the negative range. The second process that serves to reset the local environment to negative 70 is that the voltage-gated sodium channels close when the action potential reaches its peak, stopping the flow of positively charged ions into the neuron. The potassium channels remain open after the sodium channels close, and thus the outflow of potassium ions continues until the voltage reaches the resting potential, thus recharging the battery so that the axon hillock is ready to initiate another action potential. The entire process, from the time the sodium channels open until the potassium channels close, is approximately 1/millionth of a second. approximately 1 millisecond, 1,000th of a second. During this time, another action potential cannot be initiated at the axon hillock, and thus this duration is referred to as the absolute refractory period. This puts a limit on the firing rate of a neuron to about 1,000 times per second. As the positive 50 millivolt charge of the action potential reaches the terminal button, it triggers the vesicles to move towards the membrane, release the neurotransmitters into the synapse, and the process repeats itself again. Okay, so that is a very brief and hopefully clear explanation of the action potential. Take a minute to check out the links on Blackboard to the Harvard tutorial on neurotransmission. It's very helpful, and it's linked right below this video lecture.